In this video, we want to talk about the third step, the assumptions for epsilon, and we want to estimate the standard deviation as part of the assumptions, and we'll get an interpretation there for the standard deviation. So far, we've hypothesized a simple linear model, straight line model. We used the software to estimate the betas attached to that. We made some interpretations. We looked at the method of least squares. And now we're getting ready to test to see if the model works and then to actually use it with our confidence intervals in the last step. But before we do any of that, before we do any of the tests or the confidence intervals, we first have to understand the type of distribution that we're working with, and that's where the assumptions come into play. Remember our regression model. We got these points that we're seeing in our population. We take a sample. These are terrible looking points here. And we are now fitting a line through. That's a straight line there, folks. Just go with me on that. We fit a line, what they're called the least squares, or the best fitting line through those points. And really what we're asking about now, let's see if I can do a different color here. I guess black will probably work. We're trying to figure out how these points fall around that line. I guess I've switched to red and the black, but how do the points fall around the line? That's called the assumption part. And so let's go right into it. There are 4 regression assumptions. These are the ones that we're going to use in simple linear regression. These are the same 4 assumptions that we're going to use in multiple regression. The mean of the epsilons is 0. Remember, the epsilons is the error part. How much did we miss by? Oh, the real sales price is this amount, and we estimated it to be that amount. How much we missed by is called the error, and we're going to say the mean of the epsilons is 0. The epsilons are normally distributed. The variance is sigma squared. That's really not the important part. The important part the variance assumption is that it's the same, it's constant, equal variances for all the settings of the extents, or constant variances is the way we typically say it. And the epsilons are independent. I can show you 3 of these. So let's try this. All right, I can show you the assumptions on a graph. So let's get the graph here. And so we have the y-axis, we're fitting a straight line. I just figured it'd be easier to give the axis and draw it out because you see how straight my lines are when I'm working with the mouse here. All right, so think about y being the sales price of a house, x is the size. And so let's come here somewhere in the middle. Let's say that this is a 2,000 square foot home. What our modeling says is that the average sales price of all 2,000 square foot homes falls right there. Individual sales prices fall around the line. So if I just looked at my 2,000 square foot homes, we'd expect to see values that fell around the line. And our epsilons, our assumptions for the epsilons, deal with how those individual values fall around the line. We state the assumptions on the epsilons, but really it's talking about where do the y's fall. And so here's the idea. If this is the average price of all 2,000 square foot homes, wouldn't you expect to see more of the homes closer to the mean than further away? And so I'm trying to draw a heavier amount of points closer to the mean, and then occasionally you get one out here or out here. But they would start to think about them piling up. And then the picture I want to draw you, the real picture I want to draw you, actually comes away from the screen towards you right now. So I'm going to do it this way. We have 3 assumptions that I can draw in this picture. First, what we're saying is the epsilons are normally distributed, meaning that if I took a look at how these values fell, they would pile up in a normal curve. The mean of the epsilon is 0. So what I'm going to do is I'm going to draw a normal curve. I'm going to try to draw a normal curve. And that's actually probably much better than I expected. That's centered at the line. Okay, and think about this normal curve coming away from the line towards you, except you can't really see it when I draw it like that. So I'm going to draw it on an angle here. And what I'm saying is, if I looked at the price of 2,000 square foot homes and they piled them up, they would pile up and they would look like this normal curve. Again, think about this normal curve coming out at you because all of the values of x, all the sizes, and the example I'm using, they're all the prices of the 2,000 square foot homes. They all fall right there. And so there'd be this normal curve. Now, the assumptions that I'm talking about here, the epsilons are normally distributed, meaning that the prices would fall in a normal distribution. The epsilons are just how far they fall away from the line. The mean of the epsilons is 0. It means this normal curve would be centered right here. Now this curve, the 2,000 square foot homes, the variation in the prices, has some kind of variation, some standard deviation or variance. What we're saying is it's constant for all the settings that he accessed. What that means is if I came over here to say 1,500 square foot homes, that curve that you see right there, this is going to be a challenging picture to draw here, folks. I'm going to try to draw exactly the same distribution. It's a normal curve. It's centered at the line, or the mean of the epsilons is 0. The curve is centered at the line. And the variation of this curve, if I could draw it correctly, is the same as the variation here, which would be the same as the variation. Oh, this is a terrible picture already. Think about taking this curve and just duplicating it. I think I have a better picture right here. That's the picture that I'm trying to draw. I wanted to walk our way through it. I want to explain it as I was drawing it. That's why I tried to do it with the pen. What we're seeing here is that the variation, the spread, you got a normal curve centered at the line. Doesn't matter what the value of x is, but I can almost take a line here and run it along and say maybe that's the 3 standard deviation line. There's the 3 standard. Notice how they're parallel lines. You get the same picture everywhere. An example I use in class, and it's going to be hard to do in the video, but I'll talk our way through it. Imagine, if you will, you come to a door and there's a doormat on the ground outside the door. It's a welcome mat, and you decide, because you're in a real welcoming spirit, that you kick the mat. And when you kick the mat, you kick one edge of the mat, it kind of bunches up in the middle. Imagine, if you will, so here's the welcome mat on the ground, right? You decide to kick it this direction. Imagine it'll bunch up and it'll form like some kind of bunch in the middle. Well, think about there being a curve that would come up. And if you did it like this assumption is stating, this curve, if you kind of look down through the center, if you got down on the ground and put your eye down there, you would see kind of a normal tunnel. I don't know if that makes sense to you or not, but that's really the line of sight. If you could get down and look down that line in this picture, and the same thing would be true up here if I could do it in my picture. You would look down there and you see this perfect normal tunnel where the variation is the same everywhere throughout the tunnel. I showed you a picture earlier in one of the other videos of some diamond prices, and we saw the diamond prices were the picture that we saw, you might remember, they were very tight together, and then as they moved away, as we went from left to right, the variation spread. So the variation here was real tight, real tight, real tight, real tight, and then the carats got bigger, the variation in the prices got larger. That would be an example of unequal variances, not constant variation. Okay, main thing now is you need to be aware of these 4 assumptions. Mean of the errors is 0. Mean of the epsilons is 0. They're normally distributed. The variance is constant. I can't really draw you an independent error assumption. The epsilons are independent. I can't really draw a picture of that. I'll talk more about that in our multiple regression topic called residual analysis. For now, just know what the assumptions are. And then, because we're mentioning this variation, we need to go ahead and talk about it a little bit. We've looked at these 2 numbers already. When we were going to identify the least squares line, we went there. Well, right over here, the standard deviation. I want you to be able to tell me what the interpretation is. Think about it. Those pictures those normal curves, we expect, and one way of saying it, we expect most of the epsilons to fall within 2 standard deviations of the mean. Well, the mean is 0. So we expect most of the epsilons to fall within plus or minus 2 standard deviations. Okay, but go back to that picture. Look back at the picture, right? What is that standard deviation trying to talk about? How far observations fall from the line. And so the interpretation that we're going to give to the standard deviation always looks like this. We expect most of the y values, most of the sampled y values will fall within 2 standard deviations, and 2 standard deviations in this case is in thousands of dollars, of the line. Well, the line is the least squares predicted equation. So we expect most of the sales revenues in this case to fall within 2 standard deviations of their least squares predicted values. So the standard deviation starts to give us a hint as to, is this going to be all that useful? I'm predicting the price of a diamond, or I'm thinking of another example, sorry. I am predicting the sales revenue to fall within $1,200 of its predicted value. And when we say $1,200 this way and $1,200 that way. And so then we start asking questions like, is that all that good? Is that useful? And we start talking about the practical ability of the model. Is it going to be practically useful? Meaning when I predict the price of a house, am I going to say, hey, yeah, I can predict the price of that house. It's going to be between $10 and $10 million. That's not practical. No one's going to be able to use that. If I say, I can predict the price of that house, it's going to be somewhere between $240,000 and $245,000. Now it's like, ooh, that's useful. That's close. That's a pretty tight, that's a pretty accurate interval. The standard deviation is our first clue. It's not our last, but it's our first clue. So in step three is a pretty easy one. Got to know what the four assumptions are. Got to be able to state them for me. And then as part of the assumptions, you mentioned a variance. We get the standard deviation from the printout, and then I want you to be able to interpret it. And we expect most of the sample y values to fall within 2 standard deviations of their least squares predicted values. And of course, that would need to be stated in the words of the problem. So that's step 3, and then we move on to step 4. Okay, does the model work? So we're ready for it now, because if those assumptions are true, the assumptions we just talked about are true, then our confidence intervals, our test hypothesis will work like a champ. So hopefully that makes sense, and I'll come back and talk about testing the model in the next video. So long.